Okay, so it's fine. Uh, yeah, so I want to talk about slightly later, but about observation of quantum interference in Doppler-free two-photon spectroscopy and how it affects precision measurements. Before I do that, I'll just give a brief overview of what are the things we are doing in the lab or trying to do rather. So first, let me start by acknowledging the people in the lab. So this is my senior most student, Bubai Rahman, who has basically done most of the work on this precision measurement, which I will talk about. And these are three other people who are doing projects with me right now. One of them is here. And we had many sort of project students and summer students who had worked with us over the last 3 or 4 years. Yeah, so I want to say that I have a postdoc position available. Anybody interested should please contact me. And we are basically exclusively funded by DAE. And I work mostly on this precision part of the, it's not quantum metrology, but it's more like precision spectroscopy. So, okay, so this is the lab, how it looks like 3-4 months ago. And so what are the things we are trying to do? One of the primary things we want to do is we want to make heteronuclear molecules. And these are going to be lithium cesium molecules. And they have high dipole moment. And you can make them in fermionic species or bosonic species. So some of the initial things that we do, so basically start with lithium atoms and cesium atoms, laser cool them, trap them, and then associate them with some magnet association and make molecules. But what kind of things we are interested here in, at least in the next 4 or 5 years, is to look at, understand what causes losses in this molecular system. So if you trap molecules, it has been observed that there are losses. You cannot hold them forever, even if the species are non-reactive. So we would like to understand this, and because of that, we actually have a mass spectrometer in our setup. So I'll show you pictures of that. And we want to also look at what are the collision complex, if there are any collision complex, 4-body complexes which are forming during the collision. So, and we want to detect those using the mass spectrometer. And this is an apparatus which is built now, more or less. We are also interested in doing trapped ions, and we want to trap calcium, but none of this is done yet. So, and we don't even know if it's going to be calcium because we don't have lasers, but we do have an ion trap in the setup, I'll show you. And here we want to study collisions between ions, laser cool ions, and heteronuclear molecules. So here the interaction will be a charged dipole molecules, and slightly different from what I have done earlier, which is an ion and an atom, where it's just a polarizability, a sort of induced dipole interaction. We also are interested in looking at this lithium atom, lithium ion collisions. So experts like Salik will know why I'm interested in this. So these have, it's easier probably to reach the S5 collision regime in these collisions if the masses are lower. So we will be interested in that. What I'm going to talk to you about is precision spectroscopy, and this is basically done in vapor cell, nothing to do with cold atoms, and on cesium atoms, and we do high resolution spectroscopy of the cesium 7D states, which is sort of some interest for some reasons. But so I will talk mostly about this part. So this is basically the cold molecule setup. So we have, this thing is working now. We have a Siemens slower for lithium. We have a 2D mod setup which can do the cesium 2D mod, and then we load them into this 3D mod regime. So this is a CAD drawing, and this is what the apparatus looks from the top. So we have around 10 to the power minus 8 millibar. This is all when the things are operating, not the base pressures. And we slow, it's a short Siemens slower. And we have around 10 to the power minus 11. That's the upper limit. We don't know the gauge. See, this is, it has basically, so this oven right now only has lithium, but it can be, we can also put strontium. So it has 2 partitions. Similarly, here in the cesium part, we have cesium, which we are working on, but we also have dispensers for rubidium. So we can in principle, but right now what is working is basically a lithium mod and a cesium mod, right? And we have 2 actually ion traps. One is in the central region, which is very big. So the spacing between the electrode is around 15 millimeter. And here we have a small ion trap, which is 10 times lower. So the spacing between the electrode is 1.5. So here it's going to be a very strong trap. And basically, we would like to trap the atoms with a dipole trap, push them here, and do more precise experiments. We have mass spectrometers along this axis and also along this axis. So if you look at the inside of the chamber, this is what it looks like. So these are it's a 4-rod ion trap, and this is one part of the ion cell lens for one of the mass spectrometers. And at the other end, we have a detector, channeltron. We also have a mass spectrometer in this direction. So about here, there's another charge detector. So the reason is that we want to detect. It's not optimized, but it's small. I can't tell you great numbers, basically. But it's small. We have around 10 to the power 7 to 8 atoms. And it takes in the 3D mode. We have not measured anything on the 2D mode. Because we don't see, so we run at 10 to the power minus millibar in the 2D mode chamber. So very low pressure, because we don't want, so we want to trap ions, and we don't want to contaminate this with anything, basically, as much as possible, because the charges react and change species very quickly. So we want to preserve the vacuum here. But yeah, it's not very high, that I can tell you. Yeah, huge. So my pressure with everything running is below 10 to the power minus 11 here. I'll just show you a picture of the load, the decay of the lithium watt. We can see a lithium watt after it is trapped, if you shut down everything for more than 5 minutes. It stays there. So we want to preserve that, basically. Yeah, so this is the picture, and this is the plot I was telling about. So some time back, but if you keep it there, everything without all the sources off, it'll stay there for a very long time. So we have this lithium watt working now, and we are operating at very modest temperatures of the oven and very low powers of the lasers, and this is basically with a single laser which does this lithium mott and Siemens lure and everything. So this is a cesium mott. This is the image. It's partially saturated, actually. This laser we have reported for those who are interested. Is very stable. We use it. We did it because there was no such laser at 671, and this gives you 150 milliwatts from just a single laser, and you can do the whole cooling, everything, basically repumping Siemens solar with the same laser. But we also now use it for our 852 and other lasers. So and it's very stable. Okay, so that is what I wanted to say about cold atoms. Now I want to talk about precision spectroscopy. No, it's just bought from, given the part numbers in that paper. It's not air coated, it's a cheap just laser. It's very high power. The whole point is that you cannot get a laser which is 150 milliwatt, which is air coated. So Toptica guys should listen. Huh? No, we don't. So we did two lasers and beat them. It's around 360 kilohertz. Plus minus something, what around less than 500 kilohertz per second. So yeah, what I want to talk about, so this was a motivation I thought I'll give at earlier talk, but you all know now what atomic structure looks like. But what we are now interested in is measuring dipole forbidden transition. So something like hydrogen 1s to 2s would be such a transition, which is not a single photon allowed transition, but you can excite such a transition with 2 photons. And why are people interested in this? Because it's a very simple molecule, atom. You can do very accurate calculations, and historically, even people have seen that initially there was just the Dirac just the Schrodinger equation, and these two energy levels are the same, but then you include the spin, and you see that there is an energy splitting of around 11 gigahertz, which was measured actually experimentally because of the different J values here. J is just L plus S, L the orbital angular momentum, S is the spin. And then more precise experiments actually showed that these two states with same J from Schrodinger equation, or Dirac equation, you expect that they have the same energy, but they did not have the same energy. They were splitting of around 1 gigahertz, and this is the lamp shift, and this led to a Nobel Prize. Basically, everything in this slide, each step is led to one Nobel Prize. So you do more precision experiments, and you might land up with something interesting, is the idea. And then if you look at more closely, each of these electronic states is split into hyperfine states because of the interaction between the nucleus and the electron spin. Okay, so cesium is not very different from hydrogen. You all know this. This is the clock transition, but typically you will be in a laser cooling, you will be excite from S to P, and that's a 1-photon transition. It has some selection rules. In this case, delta L equal to 0 plus minus 1, and delta F is 0 plus minus 2. But if you want to excite, okay, so and how do you do spectroscopy? Typically, if you don't want to do laser cooling, you do spectroscopy. You do just absorption spectroscopy. You see a very broad line because of the Doppler broadening in a vapor shell. If you want to do better, you basically make a beam, atomic beam, and interrogate perpendicular to it. This is one of the very, very precise measurements of the cesium 6p state hyperfine splitting in an atomic beam. The other way is that if you are not looking at a dipole allowed transition, but to, let's say, this kind of forbidden transition, you can do it with 2 photons. So the idea here is I want to measure the hyperfine splitting of the 7D state of cesium. These numbers are, this is from our measurement, but it's in megahertz, so 22 megahertz, 29 megahertz, 36 megahertz. And I can excite in a vapor cell atoms from either F equal to 4 or F equal to 3, because both are more or less equally populated. If I excite, and if the atom absorbs one, and if I have the lasers counter propagating, and if it absorbs one photon from this beam and one from this one, actually the first order Doppler shift cancels. So, and this happens for any velocity of the atom. So all atoms that are in the vapor cell, with irrespective of its velocity, will contribute to the signal, and the signal will be Doppler free. You will get very narrow lines, even though the atoms are moving. And typically the idea is you excite them, and then the atoms decay, and you collect this fluorescence, and that gives you a spectrum. You scan your laser, and you might measure the hyperfine splitting. So this is the schematic. So we have to beam retro-reflect it back onto itself, and you collect the fluorescence from the side. And we have a bandpass filter and a PMT, which is detecting it. Very simple. This cell is shielded with 2 layers of new metal, and the magnetic field is below 2 milligauss. So these are the selection rules. So for 2 photon, delta F can be 0, plus minus 1, or plus minus 2. So it will basically, lots of lines will show up now. Okay, so we did this measurement. So we actually do this measurement by scanning AOM. So this is the schematic, and this is important. So what we do is we split the beam into 2, and we do a 2-photon spectroscopy first. And then we use this 2-photon spectroscopy and lock the laser on this 2-photon spectroscopy. This signal is weak, but this gives a very tight lock. Then we send the rest of the beam through another AOM, which we use to scan the frequency of the laser. And this is a very precise scan. I mean, it's basically limited by only the RF generator, and that's very precise, less than a Hertz level precision. And but the problem is that the beam deflects as it scan, as you know, the beam will deflect. So we have to make sure that the cat's eye is working properly, so the beam deflection is not much, at least not detectable, and the intensity changes. So we have to have an intensity stimulation loop. So these are the things we do, and then we have basically the light which hits this the second cesium cell is basically intensity stabilized, and it is not moving around, it's just changing its frequency, right? So we do the spectroscopy now. So this was something which we did maybe a year and a half ago, and this is the we have 2 7D states, 73/2 and 75/2. Yeah. So because you have to cancel the shift, so these two are identical, running at identical frequency. So let's say 100 megahertz. So this one is used to lock it, and this one is centered at 100 megahertz, and it is tuning it, and it can be tuned by around 70 megahertz. So 70 times 2, 140 megahertz scanning we can get with constant power. And it's a very linear scan. Okay, so this is a spectrum of the 3/2 state, and we can measure the spectrum by either exciting atoms from this ground state of cesium F equal to 3, or from the F equal to 4 transition. So this splitting that you see, you expect that the splitting should not depend on where you are exciting from, but the intensity, of course, of the relative intensities change, because these are different dipole matrix, different matrix elements, right? So that's fine. So this red is actually the data, and the yellow one is the fit. It's a very good fit, and the reason we get such high signal to noise ratio is because we are detecting this light, and this light is actually not reabsorbed back. So people have done this state measurement for earlier also, they measured this state, but they typically detect this 6p to 6s transition, but that can also get reabsorbed. So the signal to noise is lower. So we have very high signal to noise ratio. So we measured this. And this is for the spectrum for the 75/2. Same technique, now we are looking at a different transition. So now here's the interesting part. And okay, so we did this, all this, so we can vary the power and measure the stark shift, we vary the temperature, we measure the collision shift. Basically, how much the line is changing, we can measure everything, and we can extrapolate to 0 power, 0 pressure, and get you the numbers for the hyperfine splitting. So here's the plot for one example of typical data set. So this is maybe taken over 6 months, right? So different days we take data, put it on the plot, and you see this is different days, and this more or less falls within this band. And this is the average of all the data that we have ever taken, basically. And this comes out for this the splitting. This is a splitting between the 2 and the 3 states of the 73/2 state. Hyperfine splitting between levels 2 and 3. This is what we get when we excite atoms from F equal to 3. But if we excite atoms from the F equal to 4 ground state, this is what we get, 22.02. And there's a huge difference. Actually, we look at the scales. Actually, this scale is different from this. So there's a difference of around 60 kilohertz, and our measurement precision is about 6 to 8 kilohertz. So it's about a 10 sigma deviation. We expect these lines to be the same, but they are not the same. So now this was very puzzling. So actually last year we presented this, and what I'm going to tell you now is we probably right now understand why this is happening. So what is happening? Okay, so what we are doing, so I'll first give you what is happening because it's much easier for me to do this now. So if you excite atoms from F equal to 4, and you're exciting, suppose your laser is tuned to close to this transition. So the atom, and then you are detecting the light at 672 nanometer, but you are using a filter. So it does not know whether, cannot say whether it's coming from this state, this state, this state, or this state. Similarly, these splittings are small. So basically it's a broad 10 nanometer band filter. So it can only say that it's around, it is getting excited somewhere over there. So now when you put the laser here, you have the highest probability amplitude of exciting this state. But there is a finite probability amplitude of exciting this one and this one. And note that I said probability amplitude. So not just the probability. You have an amplitude of excitation here, here, and so everywhere, but with different sort of values. So right. So and then the atoms can decay to this state. So basically, what you have to look at is atom starts in some state I, ends up in state F, but it can go through different excited states E. So there are different quantum pathways through which that atom can go from this state I to this state F. So if there are different quantum pathways, to measure, to find the total probability of this transition, you have to add the amplitudes, right? And then mod square it, right? So here's the mathematics of it. This is basically what I said. So you have to first excite from I to E. So, and this excitation is not single photon, it's a 2 photon. So basically it's happened via some kind of a detuned transition through these 2 p states. So you have to write this this probability of going from I to E, and this have to sum over all the states that are contributing to this. And these are the dipole elements. So I go from I to P and P to E. And these news and mu's, don't worry about it. It is the polarization, but in our case, they are the same because we have same polarization of the incoming and the reflected beam. Then, yeah, who is, yes.
Within the Doppler, when you take that, which is closer, so there will be some weight also.
This is within the Doppler.
Thing is like 29 megahertz.
Right, right. But go back to what I said, that in the 2 photon signal, what is contributing, everything is being replaced with a very narrow line width. So yes, if all the velocities are contributing, right? So you have finite probability even for that reason that there are different velocity classes. They will also be
weight, and you have taken into account.
Yeah, we have to take into account. So actually this number is, it takes into account that also, and also your transit time, because you have some, through the laser, it will take some time, right? So that will give you some also broadening. So once it is in the state E, then it will come to this F state. And then there will be another E to F kind of a matrix element. And then you have to sum over all these states E. and then you have to take basically a mod square of that to get the final intensity. So if we do this, so what happens is that, yes, please.
You said that you can go through any state E. That's for sure correct.
Yes.
But then you said that also you don't know which state F it
Ends up
you
with.
can in principle design an experiment to measure that. So
Yeah, you will just need a filter which is very, very narrow.
yeah, but it means that
I have to
you
sum
need
over.
to sum this.
Yeah.
Not,
You have to sum if you have
Yeah,
even
okay.
yeah, we have to sum it for yes.
Yes.
So if you that's true. But that sum is coming outside my mod square.
Yes.
That's the difference. Yeah. Which ones? It's like the second order perturbation theory, basically, where you have a virtuous. Which transition? This transition or this transition? I'm adding the amplitude.
We have different plots, and so different. What do you mean? Like, of course, they're criterion. You don't know which state you went through. You don't know the intermediate.
Yeah, that's the whole point. That you don't really know which state. I mean, you're collecting the overall solution. So yeah, what you are saying would be like if you have sum of Lorentzians, and the point is the sum of Lorentzians is not the whole picture. So okay, so now I have to prove, right? So okay, so one thing is that if you do this, plot this intensity, actually what happens is that, okay, when you look at the detector, there is a detector angle dependence of fluorescence. That is just dipole emission, right? It has a theta dependence. What is theta? Theta is suppose the laser is going into the board, and I have a z axis which I have defined like this. The polarization of the laser is along this, and I have a detector which is placed at some angle with making some angle with respect to the detector. So so if you actually vary this, even for dipole transition, you will see that the intensity of the peaks will change depending on theta, but the relative intensity of the peaks will remain the same. So now what happens is that when you do this mod square, on top of that theta dependence, there is another theta dependence, and that theta dependence is something like a P2 cos theta. So basically what I'm saying is, suppose there are three, in this case there are 4 states, A plus B plus C plus D. These are the 4 amplitudes. You mod square them, and then you will have terms like mod A squared plus mod B squared and so on. And these are typically like the Lorentzian ones, but you also have terms like A, B squared, right? And these terms will go to 0 basically when your P2 cos theta is equal to 0. So, and that happens at a particular angle which is 57 degrees.
Sorry, not square.
Yeah, sorry, not square. Wow, that's nice. Yeah. Yeah, so now, so basically if earlier when we were doing this, theta was 0 in our experiment, the earlier experiment, where I showed this discrepancy. So then we went back and did experiments at different angles. So this is our earlier one. This is at theta around that magic angle, 54 degree, and this is at 90 degree. So again, the black data is the data, white one is the fit. This is the residual. This residual is at the level of, so the signal to noise is around 1000. It's a very small residual, but what I will draw your attention to is look at the pattern in the residual. You have an asymmetric pattern in the residual. For this peak, for example, on the left hand side of the peak, you have your residual is higher than 0, on the right hand side is less than 0. And then as you go to this magic angle, this residual sort of becomes more symmetric. If you go, for example, to 90 degree, let's say for example here, it has changed signs, it's flipped sign. So basically what this is telling is that this void fitting, which is a symmetric function, is not a good fit. So, and it is only a good fit at this 53 degree or 54 degree when this interference term vanishes. And then you can do a complete symmetric. So that is not all, but this, so now we have to show that, okay, so just to again be crystal clear, the excitation laser is not broadband, right? So it's not exciting everything to it, it's a narrowband laser. The line width is much smaller than the hyperfine splitting. As I told you, there is a dipole emission pattern, but the theta dependence is above that, over and above that. And the wings of the Lorentzian, you might think that Lorentzian wings we will sum and we'll get asymmetry. No, Lorentzian, that part you cannot take into account. The Voigt profile is basically symmetric. It has rings, but that will not explain this asymmetry in these peaks, right? And the important take home is that this spontaneous emission does not wash out quantum interference, right? So now I'll show you some comparisons of our experiment with theory. And this theory has no free parameter. We have taken numbers which are available, which are the theoretically calculated values for matrix elements and all. And on the top is our measured spectra in red. Again, the same color coding. Red is the data, white is the fit. Right now, we may be only interested in looking at the residual, and the blue is the residual. Same color coding for the theory. You see that if I do at 0 degree, I have an asymmetry in the residual. So I will do the same kind of fitting. I fit Voigt to the data here. I fit a Voigt profile to the simulated or theoretically calculated spectrum. And you see that if I for the theory, if I fit to a Voigt profile, I get this asymmetric residual. And look at the very nice match between what you see in the experiment and theory. So if you go to 53, you see the residuals somewhere become more or less symmetric. Here in theory, actually it's 0 because there is no noise. Experiment, you have noise. You still have some. And if you go to 90 degree, this has flipped sign compared to this one. And if you look closely, this has also flipped sign. It was more clear in the earlier figure. And same if you go from f equal to 4 to transition. This is when you excite from the other current state transition. You see there is an asymmetry which matches with theory. If you go to 53, there is very little asymmetry now in the peaks, and there is nothing in the theory, and similar at any angle. What is also reproduced is if you look at the intensity, there is a small actually. So for example, if you take this measured spectra, these have slightly different heights, and you see the theory will also reproduce that. There is a small, this peak is slightly higher than this one. Here it's slightly higher than this one. Here actually it's more or less equal. Here it's more or less equal. So it reproduces basically not everything more or less within experimental errors. So this computing these huge dipole matrix elements and summing them is not non-trivial slightly. So this is a fellow at Fritz Haber Institute. He's a postdoc there. We are working with him on this project. So now what I've done is I fit this data to the Voigt profile at different angles, and from that I find the hyperfine splitting, and I'm plotting this hyperfine splitting that we have measured as a function of the angle at which I have done the measurement. And you see our earlier measurements for this was different. So it was 22.02 and 22.08. So that's the first measurement. At different angles, it is different. And this red is the data when we collect it from exciting from the f equal to 4. And the blue one is when we do it from f equal to 3. You see, initially there is a difference, but at 53 they merge. That's because my Voigt is now a good line shape for that particular angle. Then it again overshoots, but again it matches here. But that's actually just a complementary angle. So it again matches at the complementary angle because you rotated it, right? And this is the experiment. This is the 2-3 splitting. This is the 3-4 splitting. Again, you have a small. This is a smaller split, and then this is a 4-5. Here, actually, you see that more or less they keep matching, but actually the values are different. And this is the theory. I mean, it should be theory, not simulation, but it's so. And you see that this more or less exactly reproduced in the theory. So in the theory, this is where we take the theoretical spectrum, fit it to the Voigt shape, and find out what is the hyperfine splitting. The only thing which has gone an input is some value of the hyperfine splitting. It could be whatever you put it in, right? You have to that you can take from theory also, but that and put it in, and you see that this basically matches in trend, and almost there is a quantitative match, not only just a qualitative match. We can do the same thing for the 5x2 state. I said that there are two these states, and you see again there is this look at the residuals. You see this is an experiment, this is a theory. They look very similar. Of course, the splitting is much smaller. The lines are less resolved. So it becomes difficult to in both theory and experiment to make out the pattern, but they match. And wherever you can resolve more or less, you can see that it is matching very well. And we can do the same kind of experiment comparison of the hyperfine splitting at different angles with the theory. And again, you see that they're matching quite well, except maybe in one case, right? So there is basically, I feel that there is enough evidence that what is happening is you are seeing a quantum interference in optical transition pathways, and this is in a 2-photon transition. And this is very important because the shifts are very large actually. This is a prototype system cesium. So the hydrogen people actually 1s 2s people, this will be a shift at 1 kilohertz level. This is a actually this is the largest systematic effect in our experiment. If you did not know, that was the largest systematic effect. So it's a very, in my opinion, a very important thing. And these are basically the numbers which we measure now with hyperfine splitting compared to other previous results, and we are doing maybe 20 times better than other people. And here I think theory, I think, is very difficult to calculate hyperfine splitting in theory for the 7D states. So there is agreement at some level of, but not perfect agreement. So I'll stop there, but I really would appreciate if you have comments, suggestions, criticism, and tell me if it's just wrong or something. I'm happy to know your opinion. Thank you.
And the speaker.
Okay, go ahead. Oh, beautiful. Thank you so much.
Thank you.
Very exciting. Unfortunately, almost all corrections are kind of smallish, right? What is the biggest? For line shapes. Yeah, what was the biggest?
Mine one is
Yeah.
quite large, 60 kilohertz. So, for example, if you see this one, so the easiest way for me to say this is if I measure from this ground state f equal to 3 or f equal to 4, I should measure the same splitting, right? But if you don't take into account the interference, you will see a shift of around 60 kilohertz.
But I'm not talking about the hyperfine. I'm talking about looking at the line shapes. It's always a small correction.
You want me to quantify?
Yeah. Where's the biggest? This one, yeah.
Yeah, I don't. How do I?
So well, you can see it's 4. If it's the same units, it's like 4%.
Yeah, it's not same. Yeah, it's the same units. Yeah, it's a very small.
So 4%. Unfortunately.
4%. So it's a very. It's not even 4%.
0.4%. Yeah.
In our experiment, yeah, it's like more like 1%. It seems like, but there is noise, experimental noise also included in that.
Yeah.
Right? Okay. So it's hard to quantify, but what I can tell you one thing. So the last thing that we tried to do is actually take this model, like the theory model, and try to fit this with the experimental data directly. This we tried. So you get a relatively okay fit. You reduce all this. If you do the proper fit, actually these discrepancies here you don't see it, and this residual pattern goes down. But it's very difficult to make it perfectly fit, because what is happening is when you have interference, these different intensities are which you take from theory are not, you cannot consider, they are correlated now. So if you try to do a direct fit, it works, but not like it will give you a straight line with nothing. So we have done that also. But is there a quantifier which I can say how much is the, I don't know.
Okay, this percentages.
Yeah, percentages.
The other question I had, you say 53 degrees. Why did you choose 53 degrees?
Okay, no, this I didn't choose 53. I mean, okay, so you should have done it at maybe 55. So our error is.
I want 54.7 actually.
54.7.
Yeah.
So my rotation mount is 2 degree accuracy. So this is just my miscalculation. We just did. Historically, we were doing at this thing, and then.
But it's a magic angle, right? That's why it's no interference, right?
Yeah, it's magic angle. That's right.
Yeah.
So we were doing at different steps. We are doing at 0 degree, 20 degree, 40 degree, 53 degree, 70 degree, and 90 degree. So so we could have done 55, but for some reason we did.
Oh, interesting. If I may,
but at that time we were sort of at that time we were thinking that it should be it should be something interference going on.
Finally, a question about something else. You mentioned parity violation and cesium. What are you doing in that front?
No, so the very first slide where I said, so there is a paper from this Zuba and this Australian group in 2004. They say that they can calculate the S2B amplitudes with almost as precisely as the S2S amplitudes. So they are saying that you should try to do parity violation experiments, not only on the 6s to 7s transition, but also on the, let's say, the 6s to 7D transition. So that is one of the motivations. I'm not doing parity violation, but that was, but I would like to, so one thing I would like to do is, even what I understand from Bijaya and all, that if you can measure hyperfine splitting very accurately, this can actually help them improve the theory which is required. And one of the problems is that for these states it's difficult to calculate, but if you can do an empirical measurement on different D states and then sort of extrapolate, and I mean, if there's a common factor which you can include in theory, and then there's scaling and you can match the theory, then those experiments, the PNC experiments will be benefited.
I just want to say that if you can measure parity violation and cesium, this would be fantastic. Because last measured
By Wyman.
by Kalman in 1997.
And there is controversy.
It's a shame to some experiences that nobody has.
There is another group which is trying, right? You might know Dionysus as advisor, right? He's trying to, yeah, okay.
Still have a few minutes, okay.
So can I make a comment? I have joined online. Bijaya
Yes,
Sahoo.
yes.
So okay, just one clarification is that actually that transition is 6S to 5D 3-hop. So okay, this 7D 3-hop result you need for different purpose. It is not directly related to PNC, but anyway, that is not an issue. What I wanted to ask is that the transition you showed from 6S to 7D.
Yeah.
And in the 7D state you have different hyperfine levels.
Yes.
But some of them can be M1 forbidden, right? They may not be like allowed by M1 transitions.
This is not a M1 transition. We are doing two-photon transition. It's not a
It's
single photon transition.
Okay. So I see. So it's a
But yeah,
two-photon transition.
it can be a M1 transition. You can do a single photon transition probably as well. Very weak probably, but yeah, it's possible.
Okay. Because
But
then it can have different weightage from different the population to the 70 different hyperfine levels will be different. Then that may try to resolve a little bit this kind of discrepancy. But anyway, that is one thing. Second thing I just wanted to know is when you do these measurements, but anyway, you didn't talk about that. So in the end, you are going to measure the hyperfine energy differences between two levels, right?
Correct. Yeah, these two levels. Yeah.
And then you will extract A, B, C, those
A, B, and C,
constants.
yes.
Okay.
Correct.
So
yeah.
that was okay.
That was on the last slide. I didn't know you were there. So otherwise, I would have put some.
No, I had promised you that I will.
Yeah, these are the AB values which we get, and this takes this second order correction from from in the perturbation theory, perturbation expansion.
Yeah. So those corrections, how did you estimate? That's what actually.
Yeah. So that correction is 1 kilohertz for the 7D3/2 state and around 3 kilohertz for the 5/2 state. Both are below our limit, but we still take into account those things. Yeah.
Okay. I see. Okay. So okay, maybe I'll talk to you later. So in person. Okay. Thank you.
No, I should not. So okay. So if you do the same detection with fluorescence, there will be no change. It will be more difficult in cold atoms because here we have very high density, so we can have large signals. This effect, but remember this is because we are looking at fluorescence. So, but if you can come up, if you just ionize them from the 7D state, and then this might not show up. Because it depends on theta, right? And theta is the detector angle. So if you can just ionize and collect everything, or you put detectors, fluorescence detectors on 4 pi angle, then each angle will have a different spectrum, but on an average, they will average out. Right. So so this is the dependencies on theta. Right. But in cold atoms, I don't think you will improve much. Yeah.
Yeah, but I want to make one comment.
Yes.
The fluorescence profile angle known, for example, detection of the fluorescence, and it depends upon which hyperfine level the decay is happening. So I'm not sure that it is really a quantum interference, or it is just because of there are various decay from different hyperfine levels, and they are having different profile. And then there is peak pulling happening around.
No, it's not that. So what you are saying is that there is a peak here, there is a peak of different intensity and a peak of different intensity, and there is a base here and there is a base here. So these are still sum of Lorentzians, right? The sum of Lorentzians cannot explain this. That is what I'm trying to stress. If that was the case, your residuals would be symmetric. Right? Your residuals will know. Yes.
Now, if you do another experiment, you can superposition of those hyperfine, for example, by pulse excitation.
Right, right.
And then if you observe the fluorescence as a function of time, you see beats.
Beats, you will see beats.
You see
yes,
beats.
yes.
Except if you look at the magic angle, then you don't see
The
beats.
beats, yes.
Because you can work it out that at the magic angle, those beats disappear.
Yeah.
And here it's a complementary experiment where you have a CW laser. And so what is fixed is the initial state, the final state, and the laser frequency. And so you do not have, this
Broad
actual
bands.
excitation of those states, right? But you do have these amplitudes interfering. So it's a beautiful complementarity
Yes.
to this quantum beat experiments that people used in the past, maybe to measure hyperfine by time resolved techniques.
Following up
Okay,
on
thank you.
Shankar's question, so
Ah.
in cold atoms, I think you have to take care of the trap, effect of the trap. Like if
Yeah,
you're in
yeah,
a
you have to
dipole
shut
trap,
down your magnetic
uh,
field. So
yeah,
very well.
so exactly, like if you're in an optical trap, you have to take care of the AC stark
Yes.
shift, and in the magnetic trap, you have to take care of the
Yeah.
Zeeman shift.
Well, you can do the measurement with shutting off your magnetic field,
Yeah,
switching
but
off
then
your
you have to
trap. That is
do
what people do. How
In a
people
free
do it.
space.
Yeah, in free space it's possible, but I think the signal to noise. This see the people. It's not like people have done two-photon spectroscopy for so many atoms, so many different cases. The point is you need very high signal to noise ratio, and you need otherwise it's very. So if we have done the experiment. Let's say by detecting the other way, how people have done using the 852 nanometer, the signal is 100 times weaker, and you cannot make out any interference. Yes.
What is the lifetime of that 7?
The line width is 1.7 kilohertz, so the lifetime is around 96, 97 nanosecond. 100 nanoseconds, 0.1 microsecond, however you want, around 100 nanoseconds. It's a narrower line compared to your typical D transition, S to P transition, sorry, for all the alkali atoms, which is around 6 megahertz. This is around 1.7 megahertz.
So I have another questions. If there is time, then I would like to ask. Like,
Yeah, we'll have to see.
is there in time?
We have a couple of minutes before 5:20.
Okay. Okay, yeah, you have time. Go ahead.
Okay, thanks. See, now there are several experiments, and like all of you, they don't, you don't agree with each other. Can you comment on that? What's the issue with all these
Okay,
experiments?
I think you cannot see my pointer, but okay. So the most, in my opinion, the most reliable one is that Stolnaker one, yeah, use the cursor. So this fellow, this reference 30 is most reliable. The other ones actually, I think they don't take care of systematics properly. So so either they are just not taking care of collisional shift or AC star shift. So I think that the difference is, in my opinion, because of trivial effects. Like if they did it properly, it would see. But this,
Okay,
yeah.
thank you.
I mean, but the point is nobody. So and now nobody has the sort of what is it called, precision to say whether they have interference or not. Because to say that, you have to be like at 10 kilohertz level of precision. But none of these earlier experiments were at that precision.
Okay.
Yeah.
Okay.
Yeah.
We will
Thanks.
end with that. That was a nice talk. Thank you again.